Today we're going to talk about Arnold 5.3. Arnold 5.3 is our latest major release. It will be out tomorrow, and it will feature GPU rendering as a beta feature. So I'll go over the Arnold 5.3 release, which is in itself quite a good release. I'll go over the beta GPU, and then I'll go over one last surprise announcement that we'll make today. What is Arnold, for those of you who don't know? Arnold is a production renderer, as was perfectly described by Max in the previous talk. It prides itself in simplified workflows, simplified controls. It handles complexity pretty well, as any production renderer should do. And it was acquired by Autodesk 2 years ago. Yeah. Arnold was awarded an Academy Award for its pioneering work in production rendering and physically based production rendering. And Arnold has been featured in countless films, and here is a very, very tiny sample of the different production it has been featured in the past month. So today we're going to talk about first Arnold 5.3. So first major feature that we added in Arnold 5.3 is that we rewrote the whole adaptive sampling. It is now faster and higher quality. We have a better, more effective criterion to terminate pixels. And we've improved the windowed adaptive sampling, meaning that all Arnold in progressive and non-progressive mode will have a lot less artifact when using adaptive sampling. We're getting really, really nice speedups for equivalent noise on those kind of scenes. We're getting 2x, or close enough. Of course, works in all the modes Arnold supports, including twin shading. Works well on subsurface scattering as well. Next feature that we added in Arnold 5.3 is we improved the Skydome sampling. I only have a tiny image on that, but really, like, the idea of the improved Skydome sampling is to avoid shooting rays towards surfaces that are behind the current shading point. So in this case, we have like kind of a worst case scenario, like space battle setting, where you have a powerful light source above and powerful light source under. What would happen before is that we would lose probably half the shadow rays, and we're now tracing shadow rays for Skydome in a more efficient way. Next thing we are adding in Arnold 5.3, we've improved the random walk SSS mode. So the random walk SSS is a brute force ray-traced SSS integrator. The new and improved version scatters more accurately and deeply in transparent objects, so the paths are longer and they bounce around a lot more in the shape, making a way more accurate image, especially on thin surfaces. And it has sometimes dramatic effects. So the new SSS mode is on the right. As you show, like in the area, the thin area, you get a lot more light. On those kind of scenes, you will see a dramatic effect. Like the paths are terminated, are not terminated as quickly as they were before. So, like if you look at, for example, the earlobe, see that there's a lot more energy coming in. It's because the random walk SSS simulation managed to get out of the lobe in the right place. Our artists in the beta program have been playing a lot with that, and they're super happy with it. It is not yet the default SSS mode, and that's mostly because since the random walk paths are longer, it is also quite expensive in terms of computation, and it's like we're still figuring out the mapping for this thing, but definitely check it out if you're doing a realistic skin rendering. Another thing we're adding in Arnold 5.3 is something that is long overdue. That is based on SPI's fantastic work on the subject. Our microfacets BSDF is now energy preserving. Anytime between conserving and preserving, meaning it doesn't lose energy as you increase the roughness. As you increase it, so the top row is Arnold 5.2, the second row is Arnold 5.3, and you see that as you increase the roughness on those metals, you stop losing energy as it was happening before. And other metal, it is very obvious on that image. So you can see that's the previous Arnold version, and that's the new Arnold version. And you can see lots of energy was lost due to roughness. Another thing is that we've improved the way we feed data to the Optix Denoiser. If you use the Optix Denoiser, you already know that it is very, very sensitive to the feature buffer you feed to it. For example, everything has to be normalized, everything has to be noise-free. How do you normalize an albedo contribution when you have 4 or 15 closures on a shading point? So that's the things we're working to improve the noise. And this is the same original render, the same noisy render, but just with different feature buffers, and it improves the noise quite a lot. And of course, I'm not going to list everything, but since Arnold 5.3 is a major release, there's a ton of performance improvements and bug fixes and so on. Okay, so next thing is that Arnold 5.3 includes the public GPU beta. So we've been in private beta for a year now, and we've been iterating every couple of weeks, shipping new releases. I think we've now released like 20 private beta to our users. And I'd like to thank all the private beta users, because the feedback has been invaluable in making the thing more useful for everybody. So here is how it looks. Okay, so to reiterate why we did all that, so why work on GPU Arnold? So if you're at GTC, you obviously probably have a pretty good idea, but just to reiterate, workflows are moving more and more towards real-time and interactivity, real-time look dev, doing more and more things in the viewport. And the GPU will give you the extra speed to achieve that work at more and more interactive rate, do everything in the viewport instead of waiting for renders. The other reason we're doing that is that all our users have been asking for it for years now, and we do listen to our users. And then GPUs are getting a lot bigger. An RTX 8000 has a gigantic 480 gigabytes of frame buffer, meaning that it's now possible to render scenes that before could not even touch a GPU. And the feedback we'll also get is that for small to medium facilities, it is sometimes a lot easier to scale using GPUs than CPUs. So we set out and I presented that last year, we set out 4 goals when we started working on our GPU, and I'm going to go over all those goals right now to see where we are a year after that. So the first goal was to create a single renderer. It has to be completely integrated into the Arnold ecosystem. It has to be feature compatible. We really want people to hit the ground running. People have countless Arnold scenes. They're working on current projects. We want just them to be able to download Arnold and click the GPU box, and they start running on GPU. That's our goal. So it has to be feature compatible. Pixel compatibility, I'll go more into detail into what we mean by that, and API compatibility, because Arnold is a library. So single renderer, we are in a pretty good shape. Arnold 5.3 can be switched on to GPU in every of the software we use, whether it's Maya. Here you can see it running directly inside the Arnold viewport, in the Maya viewport. 3ds Max is of course supported, but also Houdini has pretty good support for Arnold GPU, Cinema 4D, and Katana. So single renderer, we are, again, pretty good shape. Feature compatibility. So what we mean by feature compatibility is that we're not creating a preview renderer. The end goal is to support all the Arnold features. And we're targeting final frame, really. So the problem with that is that Arnold is a 20-year-old renderer and has tons of features, lots. I keep discovering some of the features today. And some features are super hard to support on the GPU, especially. So we decided first to focus on features that were useful for look dev, which conveniently is also some of the cases where the data will fit on the GPU a lot more than on final shots. So where are we in terms of feature support? So the first thing we added, and we took kind of an opposite approach from the renderment team, is we went directly for shading before anything else, really. And we added support for shading network. And we now support shading network that are, this is a standard basic shading network, and this one works on CPU and GPU seamlessly. That's the shading network for that asset. It is medium complexity. Of course, atmospheric rendering are in this scene. It is hard to see, but those are curves. We also completely ported the multiple scattering volume integrator. Works pretty well. The scene is completely shared and compatible between CPU and GPU, meaning that switching from CPU to GPU is very, very quick. And you can switch devices at any point without having to re-export the scene. And of course, if you don't use GPU, there's no overhead. Of course, if the scene is shared, everything just works. If you're using procedurals in Arnold, if you're doing instancing, everything works as usual. And then we went for the more higher-end production features. We now support light path expressions, so it is going to be doable to render final frame and do compositing in Arnold. The thing is, when we added what we call AOV support in Arnold are entirely based on light path expression. You can implement your own light path expression, or you can use the built-in ones, but in the end, it's the same system. So we just bit the bullet and ported it, and it just works. A nice showcase of what we can do with Arnold. So this, I rendered that using the asset by Saurabh Stefani yesterday. And this is kind of shows off everything that is working. Like you have the surface integrators working, the subsurface integrators working as well, lighting, shading network. So this is for the things that work. Of course, there's lots of features that we support that I won't mention because it would be really tedious. But here's the interesting thing. Those are the big missing features that we have right now. So the first thing that we're missing is out-of-core textures, and that's a big missing part. That is something that we are working on with highest priority. Second thing is OSL. OSL is a big part of Arnold. Lots of our users are using it daily. Lots of our users build pipeline over that. We have a pretty good support of OSL in Arnold. We support OSL closures. So we need to step up and implement that on GPU. And this is very much a work in progress. Next thing is OpenVDB. We do have the full volumetric logic ported in Arnold, but we now need to be able to feed data to that logic, and that's the next step. So that's where we are in terms of feature compatibility in Arnold. Now, pixel compatibility. What do we mean when we say pixel compatibility? So there's this idea of levels of pixel compatibility between CPU and GPU. The first level, which is the one we're at right now for the public beta, is what we call good enough for look dev. Really, it means that you trust the results that you're getting interactively in the viewport enough so that you can kick it to the render farm and have a matching image. That's the level where we are right now. The next level is to be able to use a given device for each shot and integrate that in a production, and it just works. That's where we want to be for the first release. Then having multiple devices working on the same shot, and then of course like the holy grail, which is fully hybrid computing using on the same frame GPU and CPU at their best, and that's where we want to be eventually. Of course, there are performance trade-offs, and do ask me the question about what are those performance trade-offs, because I won't have time to go in detail on those. But like, yeah, you want to be able to use the GPU hardware filtering, but this is lower quality than what you get on CPU. So if you would do hybrid computing, what is the direction you want to go? Splitting, Arnold CPU is a splitting path tracer, which has a very, very different convergence rate than a non-splitting path tracer. And on the CPU, for lots of constraints, we had to go with a non-splitting path tracer. So those are like problems that are pretty much work in progress, and we've been hammering at those problems for the past year. Other than that, we're still in a pretty good shape. We have very, very good matches. I would not be able to tell which one is CPU, which one is GPU, between the hardware intersector and the CPU intersector. Pretty much all the light sampling code matches at nearly floating point precision level. Sampling patterns work exactly the same on CPU and GPU. So yeah, the match is pretty good. So other examples where you would not be able to, and this is again like without touching the scenes. Like we just opened a CPU scene that was existing for a previous release, and clicked on GPU render, and it was just working. And the reason is we used mostly the same code base. So the next thing is a bit more special. We want the Arnold GPU to be API compatible, and it's pretty much the single renderer approach. Arnold is at its core, it's not a rendering engine; it's a library to build plugins that to do rendering on top of that library. And we did not even break binary compatibility with Arnold GPU. You could take, in theory, the DLL and just be able to swap the DLL if you're using Arnold. And we have the thing that is important is that we have clients that are building tools on top of Arnold, which are some of them are big. If you've seen the Image Engine video at the keynote, Image Engine has a tool that is called Gaffer. Gaffer is based on OSL and it is a lighting, look dev, interactive edit tool that uses the Arnold API, and we were able to directly drop in the Arnold version into Gaffer and turn on GPU rendering. It was just working. I'm lying slightly. I had to fix like one bug, but that was the idea. So you can build tools on top of Arnold, but you can also build tools inside Arnold. You can write shaders, you can write procedurals, you can write lots of plugins inside Arnold. Some of them will output code that will be run at render time. And that's pretty much where we want to be. We haven't opened the shader API in the public beta, but we are nearly there. This is shader that is mixing two closures. This code has been running on both GPU and CPU, being compiled for both since last year, and everything is working as expected. Some parts of the Arnold shader API are more complex to port than others, so we are still like toying the idea of exposing it or not, or going towards OSL. Those are very much work in progress ideas. Okay, so that's where we are right now in terms of having a single renderer that is feature compatible, pixel compatible, and API compatible. So we feel that at the level of where we are right now, Arnold GPU starts to be useful. We still don't recommend you to use it in production, but we urge you to test it and give feedback. So a bit more details into how Arnold is implemented. The first thing is Arnold is embracing Optix. We use Optix exclusively. We don't mix Optix and CUDA. We just use Optix exclusively. We went from that direction to benefit from the NVIDIA expertise. And there's another good reason for that is Arnold has tons of features, and as I said, and is extremely flexible. When you have tons of features, what you need to do is try to avoid paying for the features you don't use. And a good way of not paying for the features you don't use is to compile them out if you're not using them. The fact that Optix is a just-in-time compiler enables us to do that to some extent, to only pay for the cost of the feature the user is actually using, because user will understand that something is slower if they use a specific feature, to some extent. They won't understand that everything is slower because you added a feature that they don't use. So Optix being a compiler is something that we leverage a lot. The next reason for using Optix is that the Optix team is amazing. They've been super reactive. We have a great working relationship with them. We've been pushing hard to add some production features in Optix, like the motion blur specification. We work closely on them with that. We now have faster just-in-time compilation. Just-in-time compilation got out of hand at some point when we were working on Optix. And now the just-in-time compilation can be cached on disk and be reused. And they've been adding self-support recently. Of course, the next big reason to use Optix is RTX. And speaking of RTX, when you're doing production rendering, at least in the Arnold case, generally you spend 30% of your time tracing rays. If your scene is simple, it might be 50%, but the bulk of time will be shading, lighting, integration. And RTX makes the ray tracing part really, really, really small. So you can hope for a 2x speedup. But now runtime is mostly shading, and that's the biggest issue we have right now. That's something we're currently working with. But yeah, that's for production rendering, RTX is useful, definitely, but it's not the whole story. So here are some very early benchmarks. Of course, the performance in the public beta is not final. It may go up, it may go down as we add features, as we optimize. Like Arnold CPU has been optimized for the past 20 years. Arnold GPU has not. So there's lots of things that we are discovering every day. But we're getting good speedups. Those are benchmarks that we haven't done ourselves. Those are benchmarks that were done by users. So with some caveats, of course. But it shows that Arnold GPU in its early form, as it is right now, is already useful to some people. And this is a slide I showed at SIGGRAPH. That's like when we just had RTX when I did this slide. Like we had access to RTX for maybe like 8 days or something like that. So this is a nice experiment to showcase how RTX makes ray tracing a lot cheaper. This is going from 200 million shadow rays to 5 billions. And you see how the CPU is scaling. The CPU is scaling okay. You see how a GV100, which is already a pretty good GPU, is scaling. And you see how an RTX 6000 is scaling. And you can see that the increase in render time when going from 200 million shadow rays to 5 billion shadow rays on a production scene is tiny on an RTX 6000. And the fact that you have all those cheap rays is unlocking new research opportunities. Before that, if you access the source code of Arnold CPU, you see that in lots of cases, it is trying as hard as possible not to trace ray ever. Never trace ray when you can't. Do light culling, do all sorts of complex techniques to not trace rays. And on the GPU, we had to compile them out because not tracing rays, on some cases, is more expensive, just by the divergence. So the GPU renderer just traces more rays in lots of cases. So that's it for the state of the GPU public beta. And again, tomorrow, you'll be able to download the Arnold version, the Arnold 5.3 version, and install it and run it. You don't need license. You'll have watermarks, but you can try it. Which brings me to my next thing. Today, we are announcing that we are publishing the specification of the Arnold standard surface material. So what is the standard surface? The standard surface is the Arnold renderer Uber shader. It's our main shader that we use for most of our surfaces. It is production proven. It is physically plausible. We try to make it computationally efficient. And the goal is to really have a minimal set of parameters with intuitive meaning and ranges that is capable of rendering a wide variety of real-world materials. Not all materials, but most of them. Like if you can get away with like 90% of your object with that shader, we're happy with it. And you should be able to access it right now. We just put the white paper on GitHub with a reference OSL implementation. So what is our goal in doing that? First thing is that we want to have a common representation of material inside all Autodesk products. The next thing is that, like, when you exchange assets between different facilities, especially regarding to surface appearance, it is really, really hard. And different renderers and 3D engines use different shading systems, shading language, fixed function pipelines, and so on. And modeling accurately like surface appearance remains a very complex problem, and it's a topic of active scientific research. But there is a strong demand today for the industry to find a standardized material model that both covers most common use and is easy to use. So you do have today competing standards to represent surfaces, which you have Material X, OSL, MDL, but you have very, very few specifications for higher level implementations. So this is something that we are currently using. The standard surface has been in production for the past 2 years. We have pretty good support for the standard surface in the viewport in Maya and in 3ds Max, and we are now opening that to other software vendors and content providers. And definitely, our software vendors have been providing feedback in the private draft on the private draft of the white paper. This material doesn't appear out of the blue. It is inspired by a collection of great resources, the first one being AL shaders by Anders. The 3ds Max physical material was also a great source of inspiration and also makes the whole thing compatible with all scenes in 3ds Max. That material in its turn was also inspired by the algorithmic PBR model and the Brand Burley model from Disney. So this is, like, you can see that there's a convergence around a set of parameters, and the standard surface is kind of a new iteration on that convergence. So I can go into a bit more detail into how the model is described the surface. So the goal is to create a surface shading model that is able to faithfully represent a wide variety of real-world materials. So the light scattering characteristic of surfaces like metal, glass, wall paint, skin, wood, cloth, semi-transparent layers, and so on. It has to represent nearly all materials. And the whole model is what we call a layered mixture model. So you can see that some layers are under each other, and some layers cohabit at the same level. When a layer cohabits at the same level, we call that a statistical mixture. So you have to imagine the material as having flakes of one property and flakes of another property, and those are mixed at the same level. Some materials are, some lobes or some components are under each other, meaning that all the energy that is not reflected by the top layer goes to be potentially reflected by the bottom layer, and so on. And we've carefully crafted this set of layered mixtures. There's another way of representing it is in the form of closures. A closure is, at least from an Arnold or from all other renderers standpoint, a closure is kind of this anonymous object which has parameters and a type and an RGB weight. So the closure object is an object that the shader doesn't know much about it. It knows that it has parameters, a type, and a weight, and the shader will create a list of weighted closures and pass that on to the integrator. The integrator will then read that list of closures and integrate them. Some closures can be BSDFs, and to integrate a BSDF, you can either do like a full path tracing Monte Carlo integration, but you can also do a GLSL light loop. You can read from point clouds. You can do pretty much everything you want. Same for BSSRDFs, but a closure can also be a phase function for a volume. It can be emission, it can be transparency, and so on. So the shader is responsible for producing that list of weighted closures. And this is basically the translation of that model. And you can see that some operations are a statistical mix based on weight, and some operations are a mix based on the reflectance of the BSF. And that's how we ensure that a bottom layer will only reflect the energy that's been passed by another layer. And I can go into details into some of the effects that the material supports. So first, transparency. If you can look at on the corner, you have the place where the closure I'm talking about is. So transparency is your basic visibility. The transparency closure has no parameters really. It just makes the surface fully transparent at the shading point. And if you have a surface that is half transparent, that's the whole point of the statistical mix. Like a ray has a probability of going through the surface or stopping. The coat, which is kind of the top layer and sits at the same level of transparency, it's a dielectric coating with a GGX microfacet BRDF. So as a dielectric, this BRDF is not energy preserving for now, and it obeys Fresnel reflection laws. And the layer is, for now, assumed to be infinitely thin. So the remaining non-reflected light is passed directly to the underlying layer without refraction. And the reflection color is fixed to white. But the medium color can be set by the user. So you can control the color of the reflection of the layers that are under the coat, but you can't change the color of the coat itself. It's a bit tricky. An emission layer, so like having the emission layer below the coat is not a random choice, as all the choices we made. Like it enables you to model light bulb-like materials. And it's like your basic directionally uniform emission closure. Metal, we support a metallic lobe. The metallic lobe supports all sorts of parameters, including like complex Fresnel and thin film effects. And now, since Arnold 5.3, the metallic lobe is now energy preserving. Specular reflection and transmission, like they sit very, like one is below the other, obviously. It just models using a GGX microfacet dielectric BRDF, transmission and refraction. A nice and very, very complicated feature to support in Arnold GPU is the fact that the transmission layer can optionally take a volume as a parameter. So this is actually a fully multi-scattering anisotropic volumes that you're seeing that is happening below the transmission layer. And this is an actual a full volume ray march rendering. And this is why we had to port the volume ray marcher to the GPU in the first place without OpenVDB support. So really easily, that material will give you real complex glass and be able to model murky waters and all sorts of complex materials. Of course, we have also Sheen since Arnold 5.2, I guess, which is really useful to do cheap approximation for cloth, and good old diffuse reflection and transmission. Not much more to say about those ones. If you use a thin surface, you use a diffuse reflection, a diffuse transmission. And if you have a non-thin surface, you go to subsurface scattering, where you can use either the diffusion model, the random walk model, or the improved random walk model. And that's the whole extent of the material itself. So when we sought out to publish the standard surface as an open white paper, we first went to other vendors and users to get feedback. And following that feedback, we now in Arnold 5.3 modified the standard surface to add sometimes more control. We made it possible to change the transmission roughness without affecting the specular roughness, made some parameters linkable, improved the coat layer in some instances. We are really trying to have as little as possible in terms of parameters without constraining the artist too much. And it's a tricky balance to get, because you could expose 5 or 10 or 15 specular lobes if you listen to every request. And you can try to concentrate on a small set of parameters. Concentrating on a small set of parameters makes it a lot easier to author content, but can restrain you in some cases. So it is a tricky balance to get, and that's also another reason why we are publishing, is to get feedback and get the conversation going. The story doesn't stop there. As I said, material appearance is pretty much a vast area of research. Like 2 things that come in mind. First, reciprocity. That model is not, it will not be able to work perfectly in bidirectional model, because what is the reciprocal of that model? It's kind of an open problem. What happens if you see a surface from behind? What happens if you see a surface from the light? Not everything works as intended. Next thing is that we currently model the whole material as a layered mixture model, and this is obviously an approximation. Computing the actual energy that goes from one layer to another is, again, a tricky problem and an open research topic. So that's very much something that we'd like to discuss in the next iterations. So yeah, do contribute. You're free to implement that in your own renderer. And again, there's a reference implementation available. I think that's it for me. If you have any questions.